Welcome to the afternoon of today's Day of Data. We've made up some remarkable time over lunch. Sorry to cut it a little bit short, but we do want to get to these great presentations this afternoon. We're going to kick off the afternoon with the second keynote. We have Keynote McKiernan, a professor of physics, biomedical physics, and physiology, neurophysiology, and an advocate for open access, open data, and open science. She is the founder of Why Open Research, whyopenresearch.org, an educational site for researchers about sharing their work. She also blogs at emckiernan.wordpress.com. You can also follow her on @emckiernan13. And if you do get a chance to talk to Erin about the dead salmon, I encourage you to do so. She has a fantastic way of summarizing this great scientific story.
Thanks so much. Is that working? Yes. All right, great. So I promised myself I would put a timer on here. I have that tricky after lunch spot where people are happy because they've eaten, but also a little bit tired. And so I'll try to keep it lively. So what I want to do today is sort of step back a little. We've been talking a lot about open data, but I think we tend to kind of focus on that upper level and say, oh, there's all these great things we can do with open data. But when you're an active researcher and you actually decide to do this yourself, there's that moment of panic where you say, where do I start? I don't know how to actually do this. So yes, I'd love to share my data, but what are the steps involved in actually doing that? So I'm going to back up a little bit, talk about what do we mean by open data, and walk you through a little bit of my own experience in sharing my data personally. So just to start off, so the presentation is openly licensed, so feel free to take photos, tweet, do whatever you'd like with it. After the talk, I'll post it on Figshare, so you can have those slides to reuse however you'd like. So I just wanted to start off with kind of a description of what we mean by open science. So open data is really just one small part of this bigger picture that is open research and open science. So as researchers, we're producing all kinds of different outputs. We're producing articles, but those articles are just the very tiny end product of a much bigger process, this research life cycle that Brian was talking about. So when we talk about open science, yes, we have open data, but we also have open notebooks, which I'll talk a little bit about, open source, so sharing your code, and all kinds of other aspects, open peer review, open educational resources, with the idea that as educators and as researchers, we should be sharing all these products that we're producing along the way. So I'm only going to focus on open data and open notebooks and open source today, but just wanted to give you the idea that it's a much bigger space than just what we're seeing today. So the Foster Group has actually worked out what they call an open science taxonomy, which I think is fantastic. And so you can see some of the main categories they have here: open access, open data, open science evaluation, policies, tools. And we're really just going to focus on these ones I have circled here. So what do we mean by open data? What are the international standards for that, for data use and reuse? Open lab notebooks, which is a relatively new thing, but I think an emerging area of open science. And then some of the workflow and repository tools that we can use to share our work. So why open data, right? I think most of us here are convinced that open data is a good thing. But there are many different perspectives we can take as to why that's a good thing. So one is the researcher perspective. Why would I want to do this from a selfish perspective? Well, there are a few studies, mainly from Heather Pivovar, which show that if you share your data associated with a study, that study then gets more citations. So this is more visibility for the researcher and a personal benefit for them. So I think it's important for us as advocates to consider that researchers, especially in the early stages of their career, are understandably interested with their career advancement. We don't want anybody to sacrifice their career for the sake of the movement, and I don't think that's necessary. There are lots of different ways that they can share their work and be successful, and in some cases, get an edge up, get increased visibility. So that's one of the reasons why we'd like to see researchers share for their own benefit. Another one, so reproducibility. So I think that this image captures nicely what we'd like to think about in terms of reproducibility. This is from the Why Open Research Project. So these cartoons are by my dad. I teamed up with him to, yeah, it's an awesome thing to be able to team up with a family member on this project. So we teamed up, and the idea was to create very visual ways of transmitting to researchers the importance of reproducibility, the importance of open science, and some of the ways that they could benefit from sharing their own work. So on the web page, which I think you actually can't get into with the current Wi-Fi connection, I couldn't access, but we do have an image gallery, and all those images are openly licensed, so you can reuse those however you'd like. So we talked a lot today about the importance of reproducibility. One of the tenets of science is we'd like to see that not just this lab can produce this particular result, that when I take those methods and I try to do it in my own lab, that I can get the same or similar result, thereby confirming their findings. And so how can you do this if you can't figure out what they've done? So if you can't understand the protocol, if you can't understand what the data looks like, how can you go about reproducing that study? The short answer is that you can't. So we need open data for reproducibility. So this has been talked about a few times. I think, Brian, you're in part of this cartoon. So this was a great cartoon series that Makinaro did on reproducibility, the replication crisis. And so we would like to see that when we read through a paper, we check the methods, and we try to do that in our own lab, that we get a similar or the same result. But what's happening in a lot of these large-scale replication efforts is we're seeing that a very small percentage of those studies can actually be reproduced. And I think a lot of us have personal experience with this. As graduate students, you enter a lab, and they say, look, it's very easy. In a couple weeks, you just reproduce this result, and everything will be fine, and then you start with the rest of your project. But then you spend a year or 2 years or however long trying just to reproduce that result, and sometimes getting completely different results. And it's very frustrating, and it wastes a lot of time and effort and money. So what we'd like to see is an acceleration of science through data sharing. So this is an example of a study that we're trying to validate 50 high-profile cancer studies, and what they found was tremendous difficulty in getting access to the original study data. So trying to find out what they'd done, what the data looked like, so that they could then go and reproduce these studies. And there are many times where you contact those authors and they just don't respond. And so this is slowing down the pace of science. Another thing, so I really appreciated Beth's talk. So you were talking about the impact, the larger impact, beyond just academia. What is the impact of sharing data? So this is a new project called the Open Data Impact Map. And what they're doing is trying to gather together case studies, again, all over the world, about particular companies, some social justice projects that are reusing data. In a lot of these cases, it's open government data, but in some cases, it might be as well research data. And they're reusing that data, but not in an academic environment, now in a social justice or civil or public health problems type of environment. So I just pulled out a couple examples from Mexico that I think are interesting. So this is CREA, which is a project that tries to empower and encourage women to start their own businesses and to be independent. And this is particularly for women in socially and economically disadvantaged areas. So this is a fantastic project, and they're using open data as part of this project. Another example, this project is looking at what types of oil and gas mineral extraction is going on in different areas in Mexico. Is that invading on or damaging indigenous lands? How is that infecting the environment? And so they're using open data, and I think even in some cases producing their own open data to defend these lands and to promote human rights and environmental conservation in these areas. So fantastic uses of open data, and just another reason why we should be caring about this issue. So, but then as a researcher, you run into this problem. Like I said, you say, okay, so all this sounds great to me. I'm convinced. so how do I actually do this, right? And so I want to emphasize this point. Dumping a spreadsheet online is not open data. This is not what we mean by open data, right? Because dumping that spreadsheet online doesn't necessarily mean anybody else can understand those data or reuse them in any way. So how do we share our data in a way that's understandable and hopefully reusable by others? Because that's what we'd like to see. So I think the first step for me especially was to understand what are the international standards? What do we mean by open data? If we don't mean it's just dumping a spreadsheet, what do we mean? So this is the open definition from the Open Knowledge Foundation, and they say that open data and content can be freely used, modified, and shared by anyone for any purpose. So that's their definition. It sounds broad, but I think it's important to emphasize this issue of modify and reuse. So if I dump a spreadsheet out there that nobody else can understand, nobody's going to modify that, nobody's going to reuse that, that's not open data. So this is one of the international standards with respect to open data. Another one is the patent principles, and I like this because the name comes from the fact that the first draft was put together at the pub called Patent Arms in Cambridge. And so this is the group that worked on that. So they just have some very basic, but I think important recommendations to state. So the first is that if you're going to share your data, you should share it along with an explicit statement on how you want those data to be reused or what reuse you want to limit. That you should use a recognized waiver, a legal type of waiver or license that specifies the rights, the reuse rights on those data. Particularly that you should make data truly open. And that what we mean here is that there are no restrictive clauses. So it's very common to see data or even articles released under a Creative Commons license that has a no commercial restriction. And people at least intuitively think, well, yes, I'd like to limit commercial entities coming in, packaging up my materials, and reselling it. But what it does that is not an intended restriction, I think, is that there are some cases where educational institutions and even nonprofits can be considered commercial entities, and then that restricts their reuse of the data. So we don't want to start putting those types of restrictions. If possible, we want to place data in the public domain so people can reuse it, remix it, however they like, without worrying, tracking the attributions or any commercial restrictions there. And by the way, as a point of action, you can sign on to these patent principles and say that you agree with these. So step 2, you know the definition of open data. You decided you're going to share your data. You need to find a trusted repository, and you have a lot of choices. This is another thing that's overwhelming for researchers. Where do I put these data? So I've just put a few options here. Open Science Framework that was discussed this morning. GitHub is another common one, more commonly for sharing code, but you can also share data, and you can have the data and the code together, which can be advantageous. Data Dryad, Zenodo, which is run by CERN. Figshare is one that I use a lot. And the reason that I use it is because it's very easy, it's user-friendly, it's fast to upload things. And this is another important factor. If we're talking to researchers and we're trying to convince them to do something, we want that low barrier to entry. We don't want to make their workflow more complicated. We want to make it easier. I think this is something we also saw with the Open Science Framework. We want to make things easier and faster. Instead of having to visit a number of different platforms, if you have that integration, things go much smoother. So all of these platforms kind of have their different features, but they're all archiving. They have some type of preservation through locks. You get, for most of these, some type of permanent identifier that you can go back to or that people can cite. There are metrics, number of forks of your repository, how many people are looking at it, how many people are reusing and contributing to it. So any of these are good solutions for sharing data. Let's talk about formats. So you've decided you're going to share your data, you've picked your repository, and then what are you going to put in that repository? Again, we're not going to dump our spreadsheets, right? And we're definitely not going to put things in PDF. So we'll talk about that in a minute. So not everyone, it's important to recognize not everyone has a Microsoft license at their institution. These licenses are expensive. And a lot of institutions in the US and Canada and Europe may be fortunate to have those licenses, but other institutions in other parts of the world don't have that. So if you're releasing your file formats in those proprietary formats, they can't access those data. So it may be there, but it may still be inaccessible to them. So sharing in these non-proprietary formats allows everybody to open those files and work with them. So here we kind of have a chart. You've got your proprietary file formats over here, things like Microsoft Word, Microsoft Excel. And here you have kind of the equivalent. So instead of Excel, we can publish those data in CSV format. And that's something that most people should be able to open, even though they don't have a Microsoft license. And then we have also this issue of machine readability. So a PDF is not an ideal format for data, although many governments are using this. Mexico releases a lot of it. Although it's great that we release the open government data, a lot of that is in PDF format. So if you want to use it, you have to copy each row into a spreadsheet, and it takes a long time, and it's just not an efficient way of sharing those data. So thinking about file formats is something important in terms of accessibility of the data you're sharing. So Tim Berners-Lee has developed this great 5-star rating system for open data. And so as you can see, PDF falls on the end, the 1-star end of this scale. And so the idea is that, well, it's not ideal, but it's out there. So you should at least get 1 star for that. Okay, so you've shared it in some type of format, but it's not machine readable. It might be in a proprietary format. And you can't really reuse that or modify that, right? This is part of that open definition. You can't modify it. So going up to the next level, let's make it available as structured data. So 2 stars, if you've got that in some type of spreadsheet format, then now people at least can modify, play with, assuming they have the license to open those Excel files. Going up to the next level, 3 stars, so now you've got it openly licensed data, you've got it machine readable, and now you have it in a non-proprietary file format that people all over, even if they don't have that Microsoft license, can open, modify, reuse. And then you've got these higher levels that are related to adding URLs and then linking your data set to other data sets. So these are the most advanced levels. My shared data, I'm still at 3. I haven't gotten to 4 or 5 stars yet, but I think that's okay. I'm happy with 3 stars for now. But just to kind of emphasize the point that not all open data is created equal, right? So it depends how we're sharing these data, what format they're in, and how we're connecting them with other data sets that determines how reusable those data are. So we like badges here. I think we're all agreed that we like badges. And so you can get these badges and stick them on your data sets and say, hey, this is the level of compliance I have based on this 5-star system. And then people also know what they can and can't do with that data, right? So again, OL, meaning you have an open license on there, machine readable, and then an open format. So my data is currently at 3 stars out of 5. So what happens if you have data, you've collected it, and it's in a proprietary format, and you really don't have a good way of sharing it or converting it to another format? So I ran into this. We collect neural recording data, and a lot of the software that allows you to take these, to register these recordings is proprietary. And so you end up with files that other people can't open, and those licenses are ridiculously expensive. So what we did in this case was, and someone was talking about Stack Overflow at lunch, so I want to give a big shout out to Stack Overflow, because the fantastic thing about this open source community is you can go on there and say, I have this file type, I need to figure out how to make it readable to other people. How do I do that? And there's a community of people who've already figured out how to do that and are willing to share their solutions with you. So Stack Overflow can be this amazing tool for you to figure out how to do these what sound like simple things but may not be entirely trivial. So I wrote this small little piece of code, and a lot of it's copy-paste from some of the solutions that I found on Stack Overflow, and that's great. And that allowed me to put that code up with my data and say, if you don't have this particular software to open the file, you can open it with this little piece of code. And so that solved the proprietary file format issue. So even people that didn't have that, they can now just punch, and I show them how to run this little piece of code so they can open all the files. And there's no issue there. So there are workarounds you can use, and there are these great communities that are willing to help you figure out how to do this stuff. So, step 4. Create a master data log file, or in other words, show me the metadata. So again, dumping a spreadsheet online, not open data, because a lot of the time what we have in those spreadsheets are these abbreviations that nobody else but us can understand. And so in my case, there's one person in the audience I know who understands these abbreviations, but that's because we worked in the same lab. So there are these abbreviations of genetic lines that I'm using. And if I just dump that out there, nobody's going to understand what that means or how to reuse it. So I need to have some information on that. And then this file in particular has all the files that I'm going to release as part of the data set. So it has here the date for each recording, the channel or the file number that corresponds to that file that I'm going to share with you, the particular experimental condition. In this case, it's a genetic manipulation, and then all the data here. And I have to explain to you, what does burst start A mean? Do you know what that means? No, you shouldn't know what that means. I should explain that to you. So I think it's important to emphasize that your data are really not as clear as you think they are. You've been working with these data for a long time. You've been looking at them every day. They make sense to you, but they don't make sense to other people. And so you have to explain what's there so that people can reuse it. So part of that is creating what they call a README file, a detailed README file that explains exactly what's in the data set. So what is included? Does this data set correspond to a published article or a preprint? Because we want to link up those outputs. That's where we're linking open access to publications with open data that corresponds to that publication. You have to explain the overall data structure, any abbreviations or terminology that you're using that might be unusual, and explain any missing data. So in my data set, for example, I was recording a pattern of motor activity in a little Drosophila larva. And what happens is not every animal has the same amount of activity. So that means if I'm recording those bursts, not every animal in that sample has the same amount of data. And so I need to explain to people why it is that this recording has 10 bursts and this has 30 or something like that. Why are the file sets not the same size? So this is just an example. I put my README file up here on GitHub, and then I linked it and I said, all the code and data in this repository correspond to the preprint that can be found here. So I'm linking now my publication with my data set. So here's that publication. This is a preprint. I never succeeded in getting this to go through official journal review, but that's okay because it's out there. And in particular, this was a null result. So I did a genetic manipulation. It didn't have an effect, or at least a measurable effect. And I think it's important that people know that I did that study and didn't find anything, because again, there might be graduate students in labs somewhere in the world trying to do this again, and they should know that somebody's already tried it and it didn't work, right? So I put this preprint up on Piaget Preprints, which is one of the many preprint servers, and I put a note on that now says all the data and analysis code associated with this study can be found in this GitHub repository. So on my repository in GitHub, it's linked to my preprint. On my preprint in Piaget, it's linked back to my data so that everything is integrated. And I think this will stay a preprint forever, but that's okay. I'm fine with that. All right, so you've done all that. You put your data there. It's in non-proprietary format. Hopefully, you've got 3 stars. You've got your README file there. And then what you need to explain to people is at least how you analyzed it. So they may come up with another way to analyze it, but you should have some explanation, especially if you've developed special code. So with this project, I developed Python code that was specific to analyzing these type of data. And so I should explain to people what I did with that code. So one of the great tools that's developed in the last few years are these electronic notebooks. So they used to be called IPython, now they're Jupyter notebooks, but it's the same idea. So this is an open source, very interactive platform for sharing code and hopefully sharing a detailed explanation that walks people through the code and allows them to understand exactly what it does in each part. So let me see if I can show you an example here. So what I first needed to explain to people was how to access the data, how to open the files. So it sounds trivial, but it wasn't in this case. That's why I had that little piece of code that allowed them to open the file. So I needed to explain to them, okay, so first of all, you need to open the file. Here's how you're going to open it, and here's how you're going to plot it. And so that's what this explains. So I put my little command here, and that's an interactive cell. And you just press, you run the code that's in the cell, and then the output comes out here below. So here I've said, well, let's read this particular file that's in the data set. I want to read it within this time window. And they can change that time window if they'd like to view a different part of the data set. And then when I run that cell, here's what it's going to produce as an output. And the nice thing is, because it's interactive, they can change it. So they could change this file number. They can view a different one. Or they can change the window of time if they want to zoom in on one of these bursts. It's not static, in other words, right? So they can go and they can interact with those data however they'd like. All right, so they can open the files. And now I'm explaining to them with the notebook how I analyzed the data. So telling them, run this little piece of code that I have, specify the CSV files, because we have a non-proprietary file format, right? So run these files, and I'm explaining to them here that you're running a control file, and you're comparing that to one of the genetic manipulations. And then I'm saying, OK, you go through, you run this, and then poof, you get all your data right here. And they can, again, they can change the spreadsheet that they want to look at. They can change the data set. So if they think, for example, I might have picked a very neat, clean, pretty data set, then they can change this and look and see if the other data sets are that pretty, or if I'm presenting one that's not representative. So again, increasing transparency by letting them interact with the data and plot whatever they'd like to plot. So it spits out the data. And then, of course, you'd like them to be able to visualize it. So in this, I'm explaining to them, there's obviously more explanation involved here, but explaining to them, OK, so here's how we're going to plot the data, and here's how we're going to compare the two conditions, the control in black and the genetic manipulation in white. We're going to overlay those distributions and see if there's any change between the two conditions. This is where you can see it was a null effect. Those distributions are almost completely overlapping. But the great thing here is these are the same figures that are included in my preprint. So if they'd like to check exactly what I did, exactly how I created those figures, they can go back and run the same analyses and see if it spits out the same figures that I claim are the data in the preprint. So I think the message here is really that open data is reproducible science. Open science is reproducible science. Got these little, so this is GitHub, right? The octocat. I'm not sure how they came up with that logo. I'd love to know the story behind that one. And then Jupyter. So by combining my GitHub repo that has all my code, all my data, and all my explanation files, my metadata, my READMEs, I can then have my science be much more reproducible, because anybody can go in, they can access the raw and the process data, all of that's there. They can reproduce all the analysis that in my preprint I said I did. They can replot every figure from the preprint and make sure that those comparisons are what I said they are. And they can then reanalyze my data using different methods. So let's say they decide that the way that I was analyzing it wasn't necessarily the best way, and they've developed another way to do that. Or they've even written a piece of code. If I have it in GitHub, they can fork my repository. They can make their own copy. They can write another piece of code. They can reanalyze the data. And then they can send me a request to incorporate that into my own project. And that way I can have people contributing and saying, you know what, I think you didn't quite analyze it the right way. Or, hey, I analyzed it a different way. The results came out the same. And people can then feed back into this project, contribute new tools and analysis. So this is by Lorena Barber. She has this great thing called the Reproducibility PI Manifesto. And it's really these basic things that she does, kind of bringing this all together to make sure that her lab is producing reproducible science. So first of all, they have version control. So all of their code is in a repository where every time you make a change, every time you save a new file, that change is recorded. You can go back and look at the whole history. You can look at who's contributing. You don't have final, not this one, that one, final. So that type of problem is avoided. They do verification and validation on all their code, and then they publish those validation reports. which I think is fantastic. They openly license all their materials. One of the tricks she uses is, say they have figures from, figures from a study. They post those on Figshare under an open license, and then no matter where they publish afterwards, say they publish in a subscription journal, that Creative Commons license is irrevocable. And so those figures are open, and anyone can go back and reuse them regardless of where the final article gets published. So all of that is openly licensed. They post preprints. I just have the example of arXiv here, but again, we saw there's many places where you can publish that work prior to official publication. And you can even get feedback during this process. And I think there are some people that are very afraid of this. Why on earth would I put myself out there and post something before it's really finished? My perspective is on this is that I'd rather somebody come to me in this stage and say, I found an error in your paper, than come to me when I have the published version of record, and now I have to go and talk to the journal and put an official error statement or something on that article. I'd much rather that come sooner rather than later. Open code, so they share all their code openly under an open license. And then they have this web presence, the idea being that they should have a website where they're sharing these materials and where people can contact them with feedback. One of the most important things she says is she teaches all her students to do science this way. And the fantastic thing about that is hopefully we're creating this new generation of scientists that academically grow up thinking, this is just the way we do things. This is part of the normal process of science. And by the time they get into faculty positions, this hopefully will start to become the norm because they grew up that way. Open notebooks, so this is a sort of a newer development. So the idea being you're not just sharing data, but you're sharing this whole process and you're doing it in real time. So all those notebooks that you're writing in the lab what you did with that experiment for that particular day that used to then sit there on a shelf and gather layers of dust, and once that grad school left the lab, that grad student left the lab, they never got looked at again. Hopefully we can open up that process, make it more transparent, and publish these somewhere. So this is an open source malaria project. They've really been kind of pioneers in this open notebook space. And the idea here is that they share, see, I knew my timer would stop and just fail me, that they share all their science in real time. And they operate under what they call the 6 laws of open research. So all data are open, all ideas are shared, anyone can take part, so kind of increasing this equity that we'd like to see in the scientific process. No patents. They are looking for drugs that could potentially cure or slow down malaria, and they have committed to not patenting any of that, and I think that's amazing. Suggestions being the best form of criticism. This one's great. Public discussion is much more valuable than private email. And also that an open project is bigger and not owned by any particular lab. So we have a goal here. We'd like to help people that are in countries that are suffering from high rates of malaria. That has nothing to do with my personal success as a scientist. That's a global public health problem. And that's where I should be focusing my efforts rather on what's mine. So after I went through this whole process of sharing my data, and I announced on Twitter, look, you want my code, you want my data, you can have it, it's all here. I got this tweet and it said, aren't you worried someone will find something in your data that you missed and then they get the glory? And I think this is a really common fear. The fear of scooping is something that's preventing a lot of researchers from going and sharing their materials. And I did not have the perfect response to this. Rick Smith-Una did, and he said, if Aaron missed it and nobody else ever saw the data, the world missed out on the knowledge and nobody got the glory. And I think that's this perfect way of summarizing the benefits here. I've been looking at those data for a long time. If I hadn't seen it, by then I wasn't going to see it. And just to kind of further drive that home and to close with 2 of my favorite quotes. So from Peter Murray Russ from the Content Mine, you cannot assume how others will want to reuse your work. There may be all these things to do with those data that you never ever thought of. And if you don't share those, you'll never find that out. And then by Rufus Pollock from Open Knowledge, the best thing to do with your data will be thought of by somebody else. So with that, I'll close and open up to questions. Thank you very much. use my data? Not very many, actually. So the repository has a few forks. They're from people mostly that I know. One of them was my brother who decided he wanted to improve my code. So he's a programmer. So not many people have used those data. It's a very kind of obscure data set. So I was looking at a very specific tiny little mutation in a Drosophila larva, and how many people in the world are really interested in that, I don't know. But I hope someday somebody will find it useful. And for me, I think it was very useful, just the whole process of figuring out how to do that, so that when hopefully I do have a potentially more useful data set, that process will go a lot faster for me.
In what ways or how does your choice to follow these principles limit your ability to make use of commercial codes that may offer capabilities for analysis of data that are very hard to reproduce in open source applications?
So yeah, so in my lab, everything we do, everything we use is open source. Up until recently, I was running a Linux machine. I've now converted to Mac. But so everything we do is open source. And I haven't run into any limits. The most serious one was when I was figuring out how to open these recordings that I had. So that kind of area of software is very locked down by proprietary programs. But then, I went on to Stack Overflow. I found this. I solved the problem. It didn't take that long. And I really haven't found that it's been restrictive for us as researchers.
Let me just follow up. We have many chemists at Yale, for instance, who make use of our high-performance computing facilities, and they probably use half a dozen different codes that do ab initio quantum chemistry, for instance. And I think that they would argue that each code is unique in its capabilities in some way, and I suspect that they would think that they would produce less good science were they restricted to use just the one or two of them that may be public domain or open source, as opposed to having a suite of things, some of which may work better for what they're particularly focused on than others. Is that so in general terms, would that be a problem for this kind of thing?
Yeah, so I can't speak specifically to those. I don't know those, but I can imagine cases where that might be true. Also, there's also the problem of reinventing the wheel. If you know that this package already exists and does what you want, are you really going to invest the time to create an open source version of that? And who's going to compensate you for that time investment? I understand that that's an issue. So there may be moments where it's more advantageous for you to use, at least temporarily use the closed solution that's there. These are also my personal choices as to the restrictions that I put on the way we do things in the lab, but I don't mean by any sense that everybody has to do all or nothing. There is this continuum of open practices, and I think it's very important to recognize that people should do the level of sharing that they're comfortable with.
Do you have any advice for people who have data that they can't actually release? They want to do as much open as they can, but maybe they have private data that they're not allowed to release.
Yeah, so there will be data sets that for privacy concerns or for legal reasons you're not able to release, and that's okay. I would say the first piece of advice is to make sure that that's actually the case. So sometimes we tend to think that we don't have the right to share those data. Data ownership is a little bit tricky. Or we think that maybe anonymizing those data might be impossible when there might be somebody else who's figured out how to solve that problem. So I would kind of reach out to people in your field, maybe reach out to even legal in your university and ask them questions about whether, how restricted you actually are. And then if you really can't share the data, that's understandable. That happens sometimes, but you can share other parts of the process. So you can share the instruments or your analysis code or maybe some metadata, depending on whether there's sensitive information there. So sharing all the things that are related to that project that aren't necessarily the data, I think is still a great step in the right direction. If we got all researchers to do that, we'd be I don't know if we'd be here today. We'd be way better off than we are today. So yeah, I think, again, we don't want to tell people it's all or nothing. You share what you can. And if there's stuff that you can't or you're not yet comfortable with sharing, I think that's okay, and I think we should support people in those decisions.
Hi. So regarding the malaria project that you talked about, so they kind of pledged to do no patents, but that doesn't stop the other companies getting patents, right? So I mean, there is actually a lot of debate in genomics. I don't know if you're aware of it regarding this stuff. So I mean, do you have any ideas on how to do open science with this, kind of threat of the companies? Well, I mean, for example, like, human genome is kind of protected by, right now, the judges, I guess, so to speak, right? They cannot really patent like parts of human genome. Otherwise, we wouldn't be able to do any good science, right? So, I mean, what are your thoughts on this? Like, how to do open science with
Yeah, so I'll preface this by saying that I'm not a lawyer, so let's get that disclaimer out of the way. So in the case of the open source malaria project, they are posting their progress on a daily basis. They're publicly sharing their entire process and all the data, which means that, as far as I understood, that would count as prior art. So if somebody else tried to file a patent based on that, they have all the date and timestamps. They could very easily say, no, we have already done a public disclosure of this that counts as prior art. You cannot claim a patent on that. That's what I understand, at least under US law. Patent law varies a lot internationally, so there might be some exceptions to that. But there shouldn't be the case that it would be very easy for someone to just come in and co-opt all their material and patent that. I do get a lot of questions about whether commercialization is necessarily mutually exclusive with open science. I don't think that's the case. There's some great models in open source, so Mozilla being one, that they share all their code and they still manage to have a successful business model. There are companies that do that, so they release the code, but what they commercialize is their personal one-on-one advice about how to run the code or troubleshoot or whatever, and they still manage to run successful companies commercializing that aspect while making all the code free. So I think there are lots of ways, creative ways, that companies can exist, that research products can be commercialized and still be open. Yeah. More questions? Nope. All right. Thank you very much.